Okay, so for our last talk, Ben Rose, now at Duke, will be talking about the synergistic observations for Roman extragalactic transient science.
Yeah, thanks, Ori. I'd like to thank all of the organizers for giving me this opportunity and giving space for us to discuss not just what we can do with Roman, but what can be done at a more holistic view. So a lot of this talk comes from a response to a request for information. NASA and the DOE put out this request of information last year. A large group of us worked together to try to characterize some of the synergistic capabilities and needs when working together between Roman, Rubin, and Euclid. This was focused on my research topic, measuring dark energy with type 1a supernovae. But a lot of these synergies are relevant to a wide range of science topics. And so a lot of the examples are what I know, but hopefully that there's a number of examples here that are relevant to everyone. So how do we actually get to a place where our science is better than the sum of our individual surveys? So I'm gonna take it back to a simple method, and we're gonna look at just the classic 5 W's, 5 questions, 6 actually, we'll get to that. Why is this cooperation important will be where we start, but then we'll quickly look at who is participating in this, and what are these observations, and when do we need to deal with this problem, these sets of questions. Where we actually will skip because it's self-evident that these observatories will be doing this. But we'll end with sort of how can we make this happen? How do we get from where we are today to where we would like to be? So why is this important? I have 8 sort of ideas here about why this is important. Of course, this is not an exhaustive list. It's a list that I came up with a lot of help from others. So we all know that each survey has a unique set of information, and so that's important as we try to understand the universe as a whole. And as we want to use these surveys together, we need to make sure that the photometric calibration is there. Redshifts are important for many scientific cases, as well as the spectroscopy of the transient itself. We've heard a little bit about these in previous talks, as well as making sure that we have rest frame near infrared data and sort of extending the wavelengths that we are observing. These last 3 actually, with these, as we learn about our surveys and we better characterize each individual survey, we actually gain more information. So as we understand the sort of selection functions of how well our magnitude or what our limiting magnitudes are, we can better understand science. As well as when we used force position photometry, we can take sub-signal samples, sub-signal imaging and get these sort of extra information from upper limits. And finally, with source injection, we're able to look at not just the surveys, but the analysis pipelines as well. So digging a little deeper into each one of these, first, the unique information. I like to sort of classify surveys in these as 4 parameter space. So a lot of people look at the depth as sort of the main and first parameter, but also wavelength is a very close second. But these 2 just aren't the whole picture, because you would see something like Atlas down here at a limited depth, and you're like, so SDSS just supersedes Atlas. But that's not quite true, because once you add in these other parameters, such as temporal sampling, you see that Atlas on its like nightly cadence gives us a lot of different information than something like SDSS, or definitely something different than the Roman deep fields, which are going to be probably about a 5-day cadence, or DES, which is a little bit longer. And that is vastly different than Rubin's wide, fast, deep survey, which is going to be getting much closer to a 1 month cadence on the single filter repeated gap. And then finally, the fourth parameter that I like to think about a lot is the sky location and area. And these really, all of these together really relate to the total number of transients that you can observe. Photometric calibration is an important thing, particularly for dark energy. And so these uncertainties in the fluxes of the standard stars really propagate quickly to the dark energy measurements. This is a figure from Rebecca Hounsel's paper in 2018. The x-axis is sort of the precision of which we can measure dark energy. And the y-axis is ranking these systematics, mostly hardware systematics, but including some astrophysics systematics. And the length of each bar is saying like where we are now and where we need to be getting to sort of maximize the survey. And so you can see that there's a lot of work ahead and a lot of constraining power left in these 0 points, the Y and R band in this case, in this example survey, or the second and third leading uncertainty. So coordinating these stellar calibration networks allows for improvements in these cross-survey calibrations. So redshifts are important for many different science cases. We learned from Helen earlier about how they're helpful for classifications, but they're also helpful for rate measurements. In 1A cosmology, they're one of the two fundamental quantities that we need to make a Hubble diagram. And so one of the main things that we need to measure the redshift of a host galaxy is actually to find the host galaxy. But that's not always very easy. But surveys with different depths allow us to understand and characterize our host galaxy mismatch. And so in addition to that, you need coordinated follow-up because you don't want to be observing the same host galaxy multiple times for multiple different surveys. Here's a work by a grad student, Kevin, here at Duke. It should come out on the archive shortly, I hope. And so he has simulated pixel level simulations of the Roman extragalactic time domain survey. And so is able to actually start doing some of these measurements now with truth catalogs. So you can see here that most of the galaxies in the 1As were able to associate correctly. The green galaxies here are misassociation. The green points here are misassociations, but that's where the host galaxy wasn't detected. So these are hostless one transients. So there's not a whole lot we can do about that. And the ones where actually it is, the host galaxy is detected, but not associated, are just these very few orange points. I think one of the most interesting things about Roman is the possibility of getting spectroscopy of the transients with the prism and the GRISM on board. And so this is useful for transient classification. But beyond that, I'm actually really excited for the astrophysics that can be learned from spectroscopy. I got my PhD at Notre Dame, where there's a large nuclear astrophysics program. And so the fact that we saw the lanthanides in the kilonova spectra, finding the astrophysical site for the R process was a big answer to a question that started talks for 5-10 years that I was seeing all the time. So I'm excited to see what sort of astrophysics that we can learn from spectroscopy of transients in the next decade. But coming back to my science in 1A standardization, the spectra of the transients actually can help improve our standardization of type 1A supernovae. Boone et al. 2001, both A and B, sort of built a model about how you can use the spectra in standardization. So here's a spectra of two 1As where their optical standardization properties, their photometric standardization properties are nearly identical but they have differences in their spectra. So don't worry too much about the details on this plot. Basically, the x-axis is a number of sort of systematics that 1A cosmology are worried about. And the y-axis is just sort of the magnitude of those systematics. And so smaller is better. And so the SALT2 plus X1, that is our sort of standard cosmology in the blue points. This is what we get from photometry. Once you add Kyle Boone's model, the twins embedding in any sort of combination, the orange and the green, be able to reduce these systematics and improve our standardization. As discussed earlier, we can get with Roman and other observatories, maybe predominantly Rubin, you can get these broad U band or B band all the way down to H and maybe even K band light curves. And so these are great for building templates and understanding what these transients are doing in all wavelengths and all phases. And it really helps us improve the constraining power with better understandings of line of sight dust or any other sort of possible systematic. And again, coming back to 1A cosmology, we're seeing that the near infrared can actually is another way to help improve the 1A standardization process. This is Bayes SN. On the left, they looked at a number of local 1As. And if you just use the optical models and methods, you can get a scatter on the Hubble diagram of 0.136 here. But when you do the optical plus near IR model of Bayes SN, you reduce that scatter to 0.096. And then here is actually an example of that model, Bayes SN, spanning all the way from B band to H. So the last few reasons why are these sort of survey specific and understanding our surveys. So selection functions, in a magnitude limited survey, the average observed values can change as a function of redshift. There's a plot that exemplifies that from David Rubin's paper in 2015, where he was looking at the mean Hubble residual. This is true for many different parameters. And you can see that as he splits the cosmological sample into four sort of survey bins, low Z, mid Z, high Z, and high Z surveys, you'll get things like this mid Z survey where the Hubble residual is dropping down. So you could think that that is cosmology. But once you add a deeper survey on top of that, you go, oh, no. That's our selection effect of this mid Z survey and not actually a cosmological effect. Because the deeper surveys still have that sort of Hubble residual of 0. Another detail about surveys that we can learn as we work together is the use of force position photometry. So when you know the location of a transient from a deeper survey, you can do sub-threshold photometry on that position in another survey. And then so that means that even though it might be faint in sort of an optical band, if the deep images of Roman find a transient, you can still get some information. Maybe it's an upper limit, maybe it's only a couple sigma photometry, but you can still get some information in those broader wavelengths. Again, I wanted to show some more images from Kevin. Here you can see a light curve from his pixel level simulations. So if we work together enough and not just sharing catalog information, but sort of meld the pipelines together, you can inject artificial sources into all of these different pipelines, the same artificial source into every pipeline. One of the benefits of artificial source injection, there's a lot of them. One of them is understanding the sort of anomalous noise of bright galaxies. When you do subtraction on a bright galaxy with a higher local surface brightness, you seem to get extra noise. The sort of RMS on the flux So this is from the Dark Energy Survey. You can see here on the insets, the top row here is a brighter galaxy. And the residuals and the chi-squared, you sort of have a noisier pattern in your chi-squared fits. Whereas on a fainter, lower surface brightness galaxy, you have a more even, smooth chi-squared across the whole field of view, across the whole galaxy. So joint tests of artificial source injection can lead us to better characteristics of both the selection effects as well as potential photometric biases like these. So who is this all? Who's going to be a part of this? Well, of course, the main one that mirrors Roman so well and complements it in so many ways is the Rubin observatories and the LSST. But on top of that, the Euclid mission has a number of complementary aspects. Of course, JWST will be incredibly helpful for follow-up. But also Subaru, they have the new PFS. Instrument is coming online, and Subaru has an agreement with Roman to give 100 nights as a part of Japan's involvement in Roman. So these are a lot of the big players, but there's a lot more than that too. Foremost, with its multi-object spectrograph, will be incredibly helpful for follow-up observations, and so will DESI. Roman will be online during the era of the ELTs, the ELT and the 30-meter telescopes. And so we need to not forget about them. And lately I've learned a lot about how Roman can work with LIGO and Virgo, do multi-messenger astrophysics. But these aren't it. These are my list, but I know that there's going to be a lot more. So really who it is just everyone. So what are these sort of observations? They really sort of boil down to sort of three things. The fields, making sure we're all observing the same fields and possibly the same time. That we have a consistent calibration network, maybe even link it to absolute flux standards from NIST, and that we're coordinating our follow-up, predominantly the spectroscopic follow-up. So Roman's high galactic time domain survey fields are not chosen yet. This was discussed earlier this morning, but our field choices are governed by roughly these four questions. That we need it in a high ecliptic latitude. This minimizes zodiacal light, but also puts us in the Roman continuous viewing zone. We also want low dust, so that puts us towards high galactic latitude. And of course, one of the main drivers for the choices of our fields is the synergistic data sets. And finally, we need to avoid bright stars like all the other surveys. So this leaves us to two main good candidates, GOODS North, maybe even EGS, but also the Euclid Deep Field South. So looking at those calibration networks, we want to calibrate between all these different surveys. There's been a lot of works on recalibrating wide area surveys. Excalibur is one of them. This is a plot from, I'm sorry, Dan, I'm totally blanking on what you wrote. Part of Pantheon and SuperCal, that's what it was. And there's been the latest supercalifragilistic from Dylan Brout that just came out this last month. But these are all still sort of seeing roughly 10 millimag systematics between the surveys, which is quite large for the dark energy requirements that we have. Maybe it fits for some science cases, but it doesn't fit for all of them. What's actually really interesting is sort of the fact that these previous attempts at doing cross-survey calibration have focused on just visible data because that's where a lot of the supernova cosmology has been. But as we move to the infrared, we had a new element to this, a new wrinkle to this project. So
5 minutes, Ben.
Thank you. So here's just a quick cartoon diagram where the length of these boxes for these 4 different surveys represent sort of the precision of their calibration, and the heights of these boxes above the sort of base down here is their reported systematics. And so pan-STARRS and DES, working in more of the optical, are roughly on the same flux scale using Kelman standard stars and fields. Vista piggybacked on top of 2 mass, so again are roughly on the same scales. But there's this sort of systematic offset, and it's sort of unknown a little bit between these visible surveys and these infrared surveys. And so once we extend these cross calibrations to these infrared wavelengths, we're adding more complexity and it'll be trickier. So we need to get started with them. So finally, the coordinating spectroscopic follow-up. I talked earlier about what we can learn from transients and the fact that we need redshifts, but it's more than just that. This spectroscopic follow-up should also include things like what exactly is a good photometric redshift training data set. Because even though we want redshifts, spectroscopic redshifts for everything, we probably can't get spectroscopic redshifts for everything. So we need to also make sure that our photometric redshifts are as good as they can be. The last few things, sort of kilonova follow-up. This is sort of hot off the press to me. When we get the sensitivity of advanced LIGO, Roman is the only survey that can observe in every band the highest redshifts from kilonovae from advanced LIGO above a 50% threshold. Chase et al. 2021 goes into all these details about how these models work and how these light curves look. And so I don't want to take their thunder, but we need to remember the depth and the cadence that Roman gives us is actually really useful for a lot of different science cases. And not only just sort of the traditional kilonovas, but there's possibility of lensed kilonovae. So I got this slide from Graham Smith. And you can see that for Rubin in the Z band, the pessimistic example, you might be able to see it for a short period of time. With the Roman, even in the pessimistic models, we should get nice light curves of these lensed objects.
2 minutes.
Yeah. So that's most of the details, but there's still the last few questions. So when do we need to do this? Well, we need to start now. A lot of calibration work and observational strategies. I know that LSST has been working on this. They had a couple cadence notes in this last year that included making sure that LSST deep dueling fields are coordinated with both Euclid and Robin. During the surveys is going to be the time that we care about the spectroscopy of the transients, as well as sort of how we are combining these broad wavelengths and building templates and improving our 1A standardization. But even after these surveys, we can go up and get transient, we can get host galaxy redshifts. We can build our photo Z training set at that point. So how are we going to make this happen? In our response to the request for information, we were talking about maybe building a few task force, including one focused on calibration across these surveys, and one focused on spectroscopy follow-up. But also there's the need for the joint computing task force, specifically for the source injection. And the Rubin-Euclid data product, derived data products initiative, initial recommendations did actually support a joint simulation group. And so we should follow their lead and join in on that. There are a few obstacles. And I'm just gonna say that a lot of them boil down to communication. And since my time is up, I'm gonna quickly go to the summary. So why are we doing this? Because each instrument gives us unique data, and we want everyone to be working together. And so what are these? Predominantly it's contemporaneous observations, a calibration network, but it's a lot more than that. And then we need to get started on this now and improve our official communication channels between the organization. I'm going to leave up these last list of questions. I know that we have a little bit of question time now and discussion afterwards. But there'll be a lot more discussion tomorrow on synergies. And so these are sort of food for thought now, and we will discuss them at some point. Thank you.
All right, thank you very much, Ben. Let's see, I am looking in Slack and I do not see any questions. I will check because I keep, you know, Zoom doesn't update when somebody posts a new question. So I have admittedly missed a few questions, but I'm now triple checking and there are no questions in Zoom either. I'll give everyone an awkward moment of silence. All right, I don't think any questions. People are probably tired. Virtual conferences can be draining. Also, it's 5 o'clock on the East Coast. Always 5 o'clock somewhere. With that said, we do have a half hour reserved. So let's thank Ben one more time. Thank you very much. Nice talk. David Rubin has one. All right, here you go. Would a faster TOO turnaround be useful?
So earlier today, I think it was brought up that the current TOOs are roughly a 2-week trigger. So I think it really matters on what you want to do with that TOO. So for this lensed model, with more information coming later this year, it looks like with 2 weeks, I don't know how far this goes out, may not be all that useful. But if you want to use TOOs for sort of discovery, because something like this, where you really need the depth of Roman to discover the EM counterpart, then yeah, we would probably need a faster turnaround, but I don't, I guess it really does depend on what science case you want to use the TOO for.
All right.